So let's talk about scatter plots. So to make a scatter plot, you need to have 2 points. You need to have an X and a Y for each of your single points. So the most common way to make a scatter plot is you start with a Cartesian coordinate system, and then you just plot X and Y. You've done this before in high school and maybe even in middle school. And what it does is when you plot your X and Y, it actually puts just one dot on the graph. And this is an example of a scatter plot. They're just randomly there based on the data. So a scatter plot can show the direction of the relationship between the variables. So a clear direction happens when high values of one variable occur with high values of another, or low values of one variable occur with low values of another. You can also have it where high values of one variable occur with low values of another variable. You can determine the strength of the relationship by looking at a scatter plot and seeing how close the points are to a line, a power function, an exponential function, or some other type of function. For linear relationships, there's an exception. Consider a scatter plot where all the points fall on a horizontal line, providing a perfect fit. This horizontal line would show no relationship, because remember, horizontal means there's no slope. When you look at a scatter plot, you want to notice the overall pattern and any deviations from that pattern. So on the next slide, there's examples of scatter plots. So scatter plot A shows a positive, linear, strong relationship. Why? Because everything's increasing as it goes right on the x-axis and up on the y-axis. And if you can kind of imagine, there is a line there. Every dot might not be on the line, but they're pretty close to it. Let's look at B. Again, there's a strong pattern going on, but what is changing it is that one dot up in the left-hand corner. So that's going to change how we look at this data, because there's one data that's falling outside the range. For A over here, we're seeing a negative linear pattern, and it's pretty strong because when you look at it, it's decreasing from left to right. You can see that, again, we could probably draw a line between those dots, and if they're not touching, they're really close to it. For B, we're seeing a negative pattern again because they're decreasing from left to right, but we really couldn't put a line where most of the dots would touch or even be close to. So we consider this a weak pattern. So A over here now is exponential growth. Remember, exponential is where it grows with the exponential function. And you see here, they're sitting on the x-axis, and then all of a sudden it shoots up. And B is no pattern, because you really can't make sense of what's going on. Is it going up? Is it going down? So that's where we say there's no pattern. So in this chapter, we're interested in scatter plots that show a linear pattern. And linear patterns are quite common. The linear relationship is strong if the points are close to a straight line, except, remember, in the case of a horizontal line, because there's no relationship, because there's really no slope. If we think that the points show a linear relationship, we like to draw a line on the scatter plot. So the line can be calculated through a process called linear regression. So remember back on those last slides when we were looking at those strong relationships, you could almost determine to put a line in there, but how would you do it? Would you make sure some dots are there or some dots are on the line? Well, we can only calculate a linear regression if one of the variables helps explain or predict the other variable. You don't want to make a regression line for things that don't make sense. One of the classic cases is murder rates and ice cream sales. Somebody could predict those if they both go increase in number at certain times of the year. Well, they really don't have anything in common except for maybe something that most people don't think about, like murder rates and ice cream sales increase in the summer. Well, why do they increase in the summer? Because it's hot outside. So you have to make sure that your X and Y have a real common goal that you're trying to see, not that you're just throwing stuff to see if it fits. So if X is an independent variable and Y is the dependent variable, we can use a regression line to predict Y for a given X. So let's look at the regression equation, the line of best fit. Data rarely fits a straight line exactly. honestly, if you see your data fit a straight line, you might want to see if something's going on. Because in the real world, data is messy. Data doesn't want to conform to straight lines. Usually, you must be satisfied with rough predictions. Typically, you have a set of data whose scatter plot appears to fit a straight line. This is called the line of best fit or the least squared line. All right, so let's look at this one. So what we're seeing here is we have along the x-axis, we have the third exam scores, and it's the independent. Your x variable will always be your independent variable. And your y, which is the final exam scores, is your dependent variable because your third exam scores are going to stand alone. But in this case, we're making a final exam scores dependent because we're trying to see if there's a relationship between what students score on the third exam compared to the final exam. So we will plot a regression line that best fits the data. So we plotted all the lines, and the data set for this is in the chapter. So if each of you were to fit a line by eye, we'd all draw a different line. You might go, you might try to do the bottom dots or the top dots or even the middle dots. So what we use is something called a least squared regression line to obtain the line of best fit, and this makes it standardized for all of us to use the same line. Okay, so the y hat is read as y hat, that's what we call it, and it's an estimated value of y. It is the value of y obtained using the regression line. It is not generally equal to a y in the data. Okay, so what we're talking about here is this is an imaginary point on the line, so this would be y hat. So because this is the actual data value right here. So I've made a point on the line of best fit that really doesn't exist, but I'm using it as an estimate. So as you can see here, this is the actual value, and this is the value for the best fit, the y hat. So in terms of here, yo minus y hat equals EO, this is the error or the residual. It's not an error in the sense of a mistake. It's the absolute value of the residual measured by the vertical distance between the actual y and the estimated y. So basically what it's doing is it's just going in there and measuring the length between the actual data point and the predicted. And we could do this for every line, every point that we have on the scatter plot compared to the line. And we're going to see towards the end of this chapter that we actually do that. So if the observed point lies above the line, the residual will be positive. And if the line underestimates the actual value for y, if the observed data point lies below, the residual is negative, and the line overestimates the actual data value for y. Okay, so what does that mean? So what it means is this one right here is a positive number because this is a positive value, but this line is not giving this point all of the credit it deserves, kind of. And then for this one right here, this is below it, and it's overestimating what it should be. So, as again, this is the residual, this line right here. So, sum of squared errors. So, this is the Greek letter of epsilon. For each data point, you can calculate the residuals or the errors. And we did that before. You could do it y minus y hat equals your residuals or error. And remember, each error is a vertical distance. So, and if you take the absolute value and you square it, you get the sum of squared errors. Using calculus, you can determine the values of A and B that make the sum of squared errors a minimum. When you make the sum of squares minimum, you have determined the points that are the line of best fit. It turns out the line of best fit has an equation. Y hat equals A plus BX. The process of fitting the line of best fit is called linear regression. The idea behind finding the best fit line is based on the assumption that the data are scattered around a straight line. The criteria for the best fit line is that the sum of squared errors is minimized, that is, makes it as small as possible. Any other line you might choose would have a higher SSE, in the line of best fit. So again, the best fit line is also called the least squared regression line. And why is that? Because we're trying to minimize the sum of squared errors. So we're trying to minimize remember that residual, that area length, so that more dots fit with smaller amounts. Okay, so let's look at how to put this in our calculator. So you're going to go to stat, and then you're going to enter your x values in L1. And then you're going to enter your y values in L2. Okay, so this is what we're seeing. We're seeing, does a relationship exist between the year and the population within 20 minutes of Walmart in Gordon County? Okay, so we see 1980, 1990, 2000, 2003, 2008, 2013. And you see the populations here. So to create a scatter plot, go to stat. It's going to be down there, and go to plot. And then you're going to do that, you go to second and Y. Because what that does is it brings up your scatter plot. Because you see this little word right here, scatter plot. When you hit the second button, it brings that up, the blue. So turn on plot 1 and then highlight on. And then you're going to scroll over to type, and you want the first one. You see here, it looks like a little scatter plot. So you choose that one, and then your X list will be L1 and your Y list is L2. And then what you want to do is you want to change your window. So you go down here to red, and you're going to make your X minimum at least your lowest X value. Your X maximum is going to be at least your highest X value. And your X SCL is going to be a reasonable value. Sometimes it'll default for you. And then Y min is going to be your lowest Y value. Y max is going to be your highest Y value. And then Y SCL, just choose a reasonable value. Okay. And then you hit graph, and it makes your scatter plot. So ask yourself a few questions. Do you think there's a pattern within that scatter plot? Does it appear to be linear? And does it appear to be positive or negative? So that's how you make a scatter plot. But the next thing you need to do is you need to make your line of best fit. So you need to go to mode, and then you're going to scroll down to stats diagnostic and highlight on. Okay, so if you see, it's right here. So then you're going to hit stat, and you're going to go to calc, and you can go either to option 4 or 8. The book writes it in 8, and I've seen it in 4. It's whatever you are comfortable with. Basically, they're the same thing. So what you're going to do, some of the calculators, what they want you to do is your X list is L1. So how you do that is do second 1. Your L2 is second 2 to correspond with L2. So you just keep scrolling down till you calculate, and this is what it brings you up. Y equals AX plus B. Well, in this case, remember, I said that you could flip the A and the B. Because the A is next to the X, that's the slope. So A equals 1,139.14. B is negative, whoa, that's a big number, 2217922.165. Your R squared is 0.98539, and your R is 0.9926. We'll go on to what that means in just a minute. So whenever you do this, you want to go ahead and write down what R squared is and write your equation down. So the results window has additional information. So again, A for this one is the slope, Y is the B intercept. So then to write the form, you do Y equals AX plus B. So all I'm doing is plugging in what I see from the calculator. So I get my equation or my line of best fit. So how do you graph the regression line with a scatter plot? Remember that line we just did on the last screen? And what you do is you go to Y equals and you type in the regression equation, or the results. And then you hit graph. And this is what you get. You got your scatter plot, and now you have a line between it. Okay, so R squared represents the coefficient of determination. We haven't talked about that yet, but it's coming. But now you know how to get it.